We've done some pretty fun problems for the hyperbolic trig derivatives, but we have just a few more here, and they might well be the hardest, so I'm looking forward to giving them a shot here. In fact, this first one almost looks like a joke. Like, what even is that? Well, I chose it for a reason. Let's have a look. Y equals x times hyperbolic arc sine of x over 3 minus the square root of 9 plus x squared. So of course this is going to be a product rule. It's two functions of x multiplied, and then it's going to be some kind of a power rule here. So let's look at what the product rule would look like. Our u value will be x, u prime is going to be 1. V is going to be hyperbolic arc sine of x over 3. I'm getting real tired of saying that. And then v prime, did you watch the explainer video? Do you know, the link's in the description by the way, do you know the derivative of hyperbolic arc sine? You should know that it's going to be 1 over the square root of 1 plus x squared. Now, let's try this out. X, of course, in here is the input, not the same as the x in here. That's more like this is the instruction, this is the actual formula. So u prime v, that's going to be, well, right, y prime equals, just to be complete, 1 times hyperbolic arc sine of x over 3 plus v prime, 1 over the square root of 1 plus the input, which is this, x over 3 squared, but then chain rule, times the derivative of the inside here. It's going to be 1/3. I do believe that's the case. Times u, which is x. This is v prime and u, like that. I feel like that's accurate. Okay. And then we still have this part over here, so minus 1/2 the square root of 9 plus x squared to the negative 1/2 times the derivative of the inside, 2x. I still feel like something's missing here, but we'll see what happens. We'll get a look. Okay, first thing I see here is this 2 and this 1/2 just cancel out, so that's nice. We'll clean this up a little bit. Hyperbolic arc sine of x over 3 plus x over 3 root 1 plus x squared over 9 minus x over the square root of 9 plus x squared. Now what I'd like to do is see if these are actually the same, because I feel like they want it to be able to cancel here. So if I bring the 3 in here, that would be plus x over 9 times all of this. So that would be 9 plus x squared minus x over the square root of 9 plus x squared. So our entire answer is just going to be hyperbolic arc sine of x over 3. So the derivative here actually cleaned up quite nicely, but this chain rule stuff, boy, can that be tricky. So the secret to doing this derivative is, one, knowing the derivative of hyperbolic arc sine, but then paying attention to these chain rule here. It's very easy to make the mistake to not bring out a 2 or a 2x or something like that. Okay, what's the next problem? Now the last two problems here are ones that you should try a number of times. You should work through it until you can bleed the truth out of it, because not only is it impressive algebraically, it's at the core of hyperbolic derivatives. These last two here, I really, really want to stress that you should practice this. I'm not just talking out of one side of my mouth here. So let's walk through it, because I have not yet derived the derivative of hyperbolic arcsecant before. Notice I'm not including the input right now. I want to find the derivative of this. So how would you find that? because we want to find dy dx, but we don't know what to do yet. And the only way you can find derivative for this kind of thing is first you got to figure out what the heck it means. So let's reverse it. It means x equals hyperbolic secant of y. And if I take the derivative with respect to x, right, we take the d dx of both sides like this, what am I going to get? 1 equals, what's the derivative of this here? The derivative of hyperbolic secant is negative hyperbolic secant times hyperbolic tangent. And we have solved that in the explainer videos. Times the derivative of the inside, that's a dy dx out there. So all I have to do to find dy dx is divide that out. So I can say dy dx, which of course is what I'm looking for, is equal to 1 over, and I'll put the negative up top, hyperbolic secant of y and hyperbolic tangent of y. But we're looking for things in terms of x, not in terms of y. Well, I have good news for you. We already know what x is. Excuse me. Oh my, what an interruption. I say, sir. This comes right down here. So I can at least say negative 1 over x hyperbolic tangent of y, right? And then for this part, well, hyperbolic tangent and secant, they have an identity that I was going to try, but I'm almost positive it's going to work, because you can remember that tangent hyperbolic squared equals 1 minus secant hyperbolic squared. So if I square root this, that's what I get here. So I would get negative 1 over x root 1 minus hyperbolic secant squared of x. Is that right? Not 100% sure that's right. It's not right. It's x squared here, because x is hyperbolic secant of y. That's what I'm feeling there. Did you catch that? So we know this is the derivative of hyperbolic arcsecant. Now we can write this problem out. Let's try this out. So y equals hyperbolic arcsecant of e to the negative x. What's the first step here? What's the first step? I'll give you a quick second. Okay, time's up. Let's find the derivative. dy dx, which is what we want, equals negative 1 over x, the input. In a formula, the x is the input, right? It's not x. Here it's x. So we get e to the negative x times the square root of 1 minus e to the negative x squared. Is there going to be a chain rule in here? Take a look at it for a second. I feel like it is. Now, this can clean up. In fact, let's clean this up, because e to the negative x squared is the same as saying e to the negative 2x. I feel like that's true. And then we have a chain rule from the inside, which is going to be, is it negative 2e to the negative 2x? I think it's just negative e to the negative x. Chain rule from the inside here. Negative e to the negative x. Yeah, I think that's right. So how does that happen now? We get two negatives on the top, so we're going to get a positive e to the negative x over e to the negative x root 1 minus e to the negative 2x. These cancel, and our answer for dy dx is equal to 1 over the square root of 1 minus e to the negative 2x. So it cleaned up nicely again. The derivative of hyperbolic arcsecant of e to the negative x turns out to be just kind of a small square root function. Still gross, not going to lie to you, it's gross. But we're talking about hyperbolic arctangent derivative type stuff. I mean, is that even real words? What the heck is that? A lot of fun to do the algebra, though. I'm not going to lie to you. I think I've said that a couple times. I got to stop saying that. I'm at war with my mother right now because we both keep saying something stupid, and we keep saying, you know, in the middle of sentences. So if you catch me on that, you put it in the comments and shame me. Don't let me say, you know, too many times in a row. All right, next problem. For the very last hyperbolic trig question, we need to know the derivative of hyperbolic cotangent, arc hyperbolic cotangent. And if I was to say y equals arc hyperbolic cotangent of x, that would be the same as saying x equals the regular hyperbolic, if there's such a thing, hyperbolic cotangent of y. That's what inverse functions do. So if I want to go from there, what can we do here? Well, that's going to be equal to hyperbolic cosine of y over hyperbolic sine of y. Like that. That's ugly, but you know what it says. And that would be a quotient rule if I want to take the d dx of this, right? d dx, this whole thing, I get u prime v minus v prime u over v squared. It's a quotient rule. This is a quotient rule. And that's going to be 1 equals, 1 equals u prime. And we know the derivatives from the explainer videos I'm sure you watched. The derivative of hyperbolic cosine is hyperbolic sine, and vice versa. It's actually easier than regular trig derivatives somehow. It just looks scarier. Minus 2 of the same over here, and that's going to be all over the denominator squared. So I get for this one is that 1 equals 1 minus hyperbolic cotangent of y squared. And, sorry, over here is going to be a dy dx still, right? Because we're taking a derivative of a y function with respect to x. So I'm going to divide that out, and we'll say dy dx equals 1 over 1 minus hyperbolic cotangent of y squared. Yuck. But I think that's correct so far. And the only thing I want to point out here, the next part, the easy part, don't forget this, we actually have this in terms of x right now. That's right here. So we can rewrite that right away, actually, and then we can get rid of the y's, because you need it all in terms of x for it to work. That's 1 over 1 minus x squared. That's it on that, actually. So now if I want to do this problem, it's going to actually get pretty simple, because we say y equals arc hyperbolic cotangent of secant of x. Well, we can find y prime now because we just chain rule, derivative of the outside. We now know that 1 over 1 minus the input squared, that's secant of x squared, times the derivative of the inside. And derivative of secant is secant tangent. You should know that from earlier in the semester, but you can always derive it using a quotient rule, remembering that this is 1 over cosine. You can get the quotient rule out pretty quick and confirm that it's secant tangent. Right? So what are we getting so far? We're getting 1 over, well, let's put it up there. Secant x tangent x over 1 minus secant x squared. Is there a way to make this better? I don't know if there's a way to make this better. I feel like we can make this better, though. Can we simplify this? Let's give it a try. So this is a 1 over cosine times sine over cosine divided by, well, this one's going to be a minus 1 over cosine squared So if I write this as a cosine squared over cosine squared, then these can have a shared denominator. So let's try that first. That would be sine over cosine squared divided by cosine squared minus 1 over cosine squared. So I could rewrite this as a multiplier of the reciprocal instead, like that, and remove this, which allows these to disappear. Let's see if that makes it easier. That's going to equal sine over cosine squared minus 1. Are we getting warmer or are we getting colder? I feel like I want to get this out of here. Is there a way to make this better somehow? Let's think on this for a minute. Cosine squared minus 1. Now, isn't it sine squared plus cosine squared equals 1? So if I subtract 1 here and subtract sine squared, I get cosine squared minus 1 equals negative sine squared. So I can write this as sine of x over negative sine of x squared. One of these will cancel, and I'll get negative 1 over sine of x. So that is going to equal negative cosecant of x, and that is our answer. So our derivative here, after all that work, of a hideous-looking function, arc hyperbolic cotangent of secant of x, turned out to just be negative cosecant of x. And when we work backwards in Calc 2 and move up from this up to this, you're going to be glad you had this practice. But that'll end it for the problem set in this chapter section.